Memory loss rarely arrives with alarms. It doesn't announce itself loudly or strike all at once. It begins quietly, slipping into daily life in ways that feel ordinary, even harmless. A name takes longer to recall. A familiar word hides just out of reach. You walk into a room and forget why you're there. Most people brush these moments aside, blaming age, stress, or lack of sleep. But beneath these small lapses, something far more serious can be unfolding. Modern neuroscience shows that memory decline is often accelerated not by time alone, but by an invisible toxic influence most people encounter every single day. Inside the brain, billions of neurons communicate through delicate electrical and chemical signals. These cells depend on clean blood flow, stable energy supply, and a protected environment to function properly. When that environment is disrupted, neurons do not scream in pain. They slowly lose efficiency. Synapses weaken. Inflammation rises. Protective barriers break down. The earliest damage doesn't look like disease, it looks like forgetfulness. This is why memory loss can begin decades before a diagnosis ever appears, long before anyone thinks to take it seriously. What makes this threat especially dangerous is that it hides in plain sight. It doesn't come from rare chemicals or extreme exposures. It comes from everyday habits, common foods, routine conveniences, and environmental factors we've been taught to ignore. This silent poison doesn't kill brain cells overnight. Instead, it interferes with the brain's ability to repair itself. It disrupts oxygen delivery. It fuels chronic inflammation. Over time, the brain adapts to damage by lowering performance, and we misinterpret that adaptation as normal aging. The brain is not designed to decline rapidly. In healthy conditions, it has remarkable resilience. It can form new connections, strengthen memory circuits, and even compensate for lost neurons, but resilience has limits. When toxic stressors constantly attack from multiple directions, repair systems become overwhelmed. The hippocampus, the region responsible for learning and memory, is especially vulnerable. Even slight, repeated insults can shrink this area, slowing recall speed and reducing mental clarity. One of the most troubling aspects of this process is how early it begins. Research shows that memory-related changes can start in midlife, sometime earlier, long before any clinical symptoms are recognized. At that stage, damage is still reversible. Blood flow can improve. Inflammation can calm. Neural connections can be restored. But only if the source of damage is identified and removed. Ignorance allows the poison to keep working silently year after year. This is why understanding the root cause matters more than memorizing brain exercises or chasing supplements. If the brain is constantly exposed to harmful triggers, no amount of mental training can fully protect it. The real solution starts with awareness. When you recognize that memory loss is not random, not inevitable, and not purely genetic, you regain control. The brain responds powerfully to changes in its environment. Remove the threat, and healing mechanisms awaken. Consider how often modern life pushes the brain into survival mode. Persistent inflammation, unstable blood sugar, disrupted sleep rhythm, and reduced oxygen delivery all place stress on neural tissue. Each factor alone may seem manageable, but together they create a toxic internal landscape. The brain prioritizes survival over performance. Memory becomes a luxury it can no longer afford. This shift happens gradually, quietly, without pain, making it easy to miss. The most alarming truth is that many people actively consume or absorb this poison while believing they are making healthy choices. Marketing, misinformation, and outdated guidelines have blurred the line between nourishment and harm. What was once considered safe is now understood to interfere with brain chemistry and accelerate cognitive aging. The gap between perception and reality is where damage thrives. Yet the story is not one of fear, it is one of precision. When science identifies a hidden threat, it also reveals a path forward. The brain does not need extreme interventions to recover. It needs the right conditions, clean circulation, reduced inflammation, stable metabolic signals. When these are restored, memory does not merely stop declining, it can improve. Focus sharpens, recall strengthens, mental fatigue lifts. Memory loss is not a sudden collapse. It is a slow conversation between the brain and its environment. Every day, signals are sent either supporting neural health or undermining it. Once you learn to recognize the silent poison shaping those signals, the process that once felt inevitable becomes measurable, understandable, and changeable. Memory loss does not usually arrive as a dramatic moment that forces attention. It slips into life quietly, disguised as distraction, tiredness, or the pressure of a busy routine. People begin to notice small changes that seem harmless, forgetting where keys were placed, struggling to recall a familiar name, reading the same paragraph without absorbing it. These moments are often dismissed as stress or age, but neuroscience reveals that this gradual fading is rarely random. In most cases, memory decline begins silently through repeated exposure to everyday factors that slowly undermine brain function. The brain is highly sensitive to its environment. It depends on clean blood flow, balanced chemistry, and stable energy to maintain memory circuits. When these conditions are disrupted, neurons do not fail all at once. Instead, communication between cells becomes less efficient. Signals take longer to travel. Connections weaken. This early stage does not feel like illness, it feels like mental fog. Because the change is subtle, people adapt without realizing anything is wrong, allowing the underlying damage to continue unchecked. What makes this process especially dangerous is familiarity. The exposures that contribute to memory loss are not rare toxins or extreme conditions. They are woven into modern daily life. Certain dietary patterns, environmental pollutants, chronic stress responses, poor sleep cycles, and metabolic imbalances repeatedly send harmful signals to the brain. Each exposure alone may seem insignificant, but together they create a constant low-grade assault on neural tissue. The brain, designed to protect itself, shifts into a defensive mode that prioritizes survival over performance. In this defensive state, the brain reduces energy spent on higher cognitive functions like memory formation and recall. The hippocampus, a critical center for learning and memory, is particularly vulnerable. It has a high demand for oxygen and nutrients, making it sensitive to disruptions in blood flow and inflammation. Over time, everyday exposures that reduce circulation or increase inflammatory signals can shrink this region. The result is not sudden memory loss, but a slow erosion of mental sharpness that unfolds over years. Because this process happens gradually, it is easy to misinterpret as natural aging. However, studies comparing populations with different lifestyles show that cognitive decline is not uniform across age groups. Some individuals maintain strong memory and clarity well into later life, while others experience decline decades earlier. The difference is often traced back to daily exposures rather than genetics. This means memory loss is not simply something that happens to people, it is something that develops in response to conditions. Another reason this silent decline goes unnoticed is compensation. The brain is remarkably adaptable. When certain neural pathways weaken, others temporarily take over. This allows a person to function normally while damage continues beneath the surface. By the time memory problems become obvious, a significant portion of neural reserve may already be compromised. At that stage, intervention becomes more difficult, though not impossible. The silent nature of this process also affects motivation. People rarely feel urgency to protect their memory when symptoms are mild. There is no pain, no clear warning signal, no immediate consequence. This allows harmful exposures to become habits. The brain becomes accustomed to operating below its full potential, and the individual adjusts expectations accordingly, believing that slower recall or mental fatigue is simply part of life. Scientific research now shows that many of these everyday exposures trigger chronic inflammation in the brain. Inflammation is meant to be a short-term protective response, but when it becomes constant, it interferes with synaptic communication, Memory relies on precise timing and coordination between neurons. Inflammatory chemicals disrupt this timing, making recall slower and less reliable. Over years, this inflammatory environment accelerates cognitive aging. Blood sugar instability is another common factor. The brain consumes a large portion of the body's energy, and it requires steady fuel. Repeated spikes and crashes in blood glucose send stress signals to neurons, damaging their ability to store and retrieve information efficiently. This does not feel like poisoning, yet the effect on memory is cumulative and profound. The most important realization is that because this process is driven by everyday exposures, it is also influenced by everyday choices. Memory loss that begins silently does not have to continue silently. When harmful signals are reduced, the brain's natural repair systems can re-engage. Neuroplasticity allows new connections to form, inflammation to calm, and circulation to improve. The brain responds not to age, but to the environment it is given, and when that environment changes, the trajectory of memory can change with it even after years of unnoticed decline. What makes memory loss so deceptive is that the real driver often remains hidden. A toxic influence can operate silently inside the body, never producing immediate pain or obvious illness, yet steadily accelerating the breakdown of memory. This hidden poison does not attack the brain in a dramatic way. Instead, it works by slowly increasing inflammation and weakening the delicate connections that allow brain cells to communicate. By the time memory problems are noticed, this process may have been active for years. The brain relies on precise communication between neurons. Memories are not stored in a single location. They are encoded across networks of cells that fire together in carefully timed patterns. Inflammation disrupts this timing. When inflammatory molecules are constantly present, neurons struggle to send clear signals. Messages become distorted or delayed. This is why people often describe early memory loss as feeling foggy or unfocused rather than completely forgetful. The information is still there, but access to it becomes unreliable. Chronic inflammation in the brain rarely starts in the brain itself. It is usually driven by signals coming from the rest of the body. Poor metabolic health, ongoing stress, disrupted sleep, and exposure to environmental toxins all send inflammatory messages through the bloodstream. The blood-brain barrier is designed to protect the brain, but it is not impenetrable. Repeated exposure to inflammatory signals weakens this barrier, allowing harmful molecules to enter and amplify the damage. As inflammation rises, synapses begin to suffer. Synapses are the tiny gaps where neurons exchange information, and they are essential for learning and memory. Inflammatory chemicals reduce synaptic flexibility, making it harder for the brain to strengthen connections in response to new experiences. This process directly interferes with memory formation. Learning becomes slower, retention becomes weaker, recall becomes effortful. Another way this hidden poison accelerates memory loss is by interfering with the brain's energy systems. Neurons require a constant supply of oxygen and glucose to function. Inflammatory processes reduce blood flow and impair the ability of cells to use energy efficiently. When neurons are underpowered, they prioritize essential survival functions over higher cognitive tasks. Memory, concentration, and creativity are among the first abilities to decline. Oxidative stress is closely linked to inflammation and plays a major role in this process. Free radicals are unstable molecules produced during normal metabolism, but their levels rise dramatically in inflammatory environments. These molecules damage cell membranes, proteins, and DNA within neurons. Over time, oxidative stress weakens neural structures, making them more vulnerable to further injury. This damage accumulates slowly, reinforcing the cycle of inflammation and cognitive decline. The hippocampus, a region deeply involved in memory processing, is particularly sensitive to inflammatory and oxidative damage. It contains a high concentration of receptors that respond to stress hormones and inflammatory signals. Prolonged exposure to these signals can reduce the growth of new neurons in this area. When neurogenesis slows, the brain loses one of its key tools for maintaining memory throughout life. What makes this process especially dangerous is that it often feels invisible. Inflammation does not cause sharp pain inside the brain. There is no immediate feedback to warn that memory circuits are under attack. Instead, the effects appear gradually as subtle changes in mental performance. People may feel mentally tired more easily, struggle with multitasking, or find it harder to focus in distracting environments. These signs are easy to ignore or rationalize. Modern lifestyles unintentionally fuel this hidden poison. Highly processed diets, irregular sleep schedules, constant low-level stress, and sedentary behavior all contribute to systemic inflammation. Even when someone feels generally healthy, these factors can quietly increase inflammatory markers that affect the brain. The absence of obvious illness creates a false sense of security while neural damage continues. Over time, weakened brain connections become more vulnerable to additional stressors. A minor illness, a period of poor sleep, or emotional strain can suddenly reveal underlying memory problems that seem to appear out of nowhere. In reality, these problems were developing gradually, masked by the brain's ability to compensate. The critical insight is that memory loss accelerated by inflammation is not an unavoidable consequence of aging. It is a biological response to a toxic internal environment. When inflammatory signals are reduced, synaptic function can improve, blood flow can recover, neural communication can become more efficient. The brain is constantly responding to the signals it receives, and when those signals shift away from toxicity, the momentum of memory decline can slow, stabilize, and in many cases begin to reverse. One of the most unsettling realities of memory decline is how early it truly begins. Long before confusion, disorientation, or serious forgetfulness appear, subtle damage is already taking place in a small but critical region of the brain. The hippocampus, responsible for forming new memories and organizing information, is often affected years or even decades before symptoms become obvious. This early damage goes unnoticed because it does not immediately disrupt daily functioning, yet it quietly sets the stage for future cognitive decline. The hippocampus plays a central role in learning, memory consolidation, and spatial awareness. Every time new information is absorbed, this structure helps encode it and determine how it will be stored. Because of its high activity level, the hippocampus has an enormous demand for oxygen and nutrients. This makes it uniquely sensitive to any condition that reduces blood flow, increases inflammation, or disrupts energy metabolism. Even mild, repeated stressors can affect its structure and performance over time. Scientific imaging studies have shown that changes in hippocampal volume can occur long before clinical memory loss is diagnosed. These changes are subtle at first, often measured in fractions of millimeters, but their impact is significant. As hippocampal cells lose efficiency or shrink, the brain struggles to form strong, lasting memories. Information may be learned, but not retained. Experiences may feel familiar yet lack detail. These early signs are often mistaken for distraction or lack of interest. One reason hippocampal damage goes undetected is the brain's ability to compensate. Other regions temporarily assist with memory tasks, masking deficits. This compensation creates the illusion that everything is normal, even as the hippocampus becomes increasingly strained. The individual may notice they need to work harder to remember things, but performance remains acceptable. This period of silent decline can last for years, allowing damage to progress without intervention. Stress plays a powerful role in this process. The hippocampus contains a high density of receptors for stress hormones. When stress becomes chronic, these hormones remain elevated, interfering with the growth and survival of neurons in this region. Over time, prolonged exposure reduces the formation of new neurons and weakens existing connections. This does not cause sudden memory loss, but gradually erodes the brain's capacity to adapt and learn. Inflammation further accelerates hippocampal vulnerability. Inflammatory molecules disrupt communication between neurons and interfere with synaptic plasticity, the mechanism that allows memories to form and strengthen. Because the hippocampus is central to this process, it suffers disproportionately. Inflammatory environments also impair the clearance of waste products in brain tissue, increasing cellular stress and damage. Another critical factor is reduced neurogenesis. Unlike many brain regions, the hippocampus continues to produce new neurons throughout adulthood. This ongoing renewal is essential for memory flexibility and learning. Early damage suppresses this process. When the birth of new neurons slows, the brain loses an important source of resilience. Memory becomes less adaptable, more rigid, and more prone to failure under pressure. What makes early hippocampal damage especially dangerous is that it alters how the brain processes information without triggering alarm. People may find it harder to remember names, sequences, or recent events, while long-term memories remain intact. This pattern creates confusion and denial. The person feels capable yet frustrated, sensing change but lacking clarity about its cause. Lifestyle factors strongly influence this early damage. Poor sleep reduces hippocampal activity and interferes with memory consolidation. Blood sugar instability deprives neurons of consistent energy. Lack of physical movement reduces blood flow and oxygen delivery to brain tissue. Each factor alone may seem minor, but together they create conditions that strain the hippocampus daily. Environmental exposures also contribute. Certain chemicals and pollutants increase oxidative stress and inflammation, further burdening this sensitive region. Because exposure is often chronic and low-level, the damage accumulates quietly. There is no single moment when memory fails, only a gradual weakening of the systems that support it. The tragedy of early hippocampal damage is not just that it leads to late memory loss, but that it is often reversible in its early stages. The hippocampus responds positively to improved circulation, reduced inflammation, stable energy supply, and restorative sleep. Neural connections can strengthen, and neurogenesis can increase when conditions improve. The window for the intervention exists long before symptoms form. Attention, but only awareness can open that window, allowing the brain the opportunity to recover and preserve memory function before decline becomes. Deeply entrenched modern life has reshaped the environment in which the brain must function, often in ways that are invisible yet deeply influential. Many everyday habits that feel normal, convenient, or even productive quietly create a harmful internal brain environment. These habits do not cause immediate damage that can be felt or measured easily. Instead, they subtly alter blood flow, metabolism, inflammation, and neural signaling, gradually pushing the brain toward a state where memory and cognitive clarity are harder to maintain. One of the most powerful influences comes from constant stimulation and mental overload. The brain evolved to handle periods of focused attention followed by rest. Modern routines rarely allow this rhythm. Continuous screen exposure, rapid information switching, and persistent notifications keep the brain in a state of alertness. This prolonged activation of stress pathways increases the release of stress hormones which, over time, interfere with memory formation and reduce the brain's ability to recover. Sleep disruption is another critical factor. Quality sleep is not simply rest, it is an active process during which the brain consolidates memories, clears metabolic waste, and resets neural circuits. Irregular sleep schedules, artificial light exposure at night, and insufficient deep sleep interrupt these processes. When memory consolidation is impaired night after night, information learned during the day fails to stabilize. The result is not immediate forgetting but a gradual weakening of recall and learning efficiency. Dietary patterns common in modern lifestyles also play a central role. Highly processed foods often cause rapid spikes and crashes in blood sugar, creating metabolic stress for neurons. The brain depends on a steady energy supply, and instability forces it into a reactive mode. Over time, This metabolic strain increases inflammation and reduces synaptic plasticity. Memory formation becomes less reliable, and mental stamina declines. Physical inactivity further compounds the problem. Movement is one of the most effective ways to increase blood flow and oxygen delivery to the brain. A sedentary lifestyle reduces this circulation, depriving neurons of nutrients they need to function optimally. Regular movement also stimulates the release of growth factors that support neural health and memory. Without it, the brain's maintenance systems become less active, accelerating cognitive aging. Chronic low-level stress has become normalized in modern culture. Deadlines, financial pressures, and constant connectivity keep the nervous system in a heightened state. This ongoing stress response alters brain chemistry, promoting inflammation and suppressing the growth of new neural connections. Memory suffers because the brain prioritizes short-term survival over long-term learning and recall. Environmental exposures add another layer of risk. Air pollution, household chemicals, and other toxins can enter the body through breathing, skin contact, or food. These substances increase oxidative stress and inflammation, affecting brain tissue over time. Because exposure levels are often below immediate danger thresholds, their cognitive impact is rarely considered, yet their cumulative effect can be significant. Even hydration habits influence the brain environment. Mild, chronic dehydration reduces blood volume and thickens circulation, limiting oxygen delivery to neural tissue. This subtle change can impair attention and short-term memory without causing obvious physical symptoms. Many people live in this state daily, unaware that their brain is operating under less than ideal conditions. Social and emotional factors also shape brain health. Isolation, lack of meaningful interaction, and reduced novelty limit cognitive stimulation. The brain thrives on challenge and connection. When routines become repetitive and socially restricted, neural networks associated with memory receive less activation. Over time, underused circuits weaken, making recall slower and less precise. What makes these lifestyle factors particularly dangerous is their combined effect. Each habit alone may cause only mild strain, but together they create a persistent internal environment that is hostile to memory. The brain adapts by lowering performance expectations, conserving energy, and reducing investment in memory systems. This adaptation feels like normal aging, but it is largely a response to conditions rather than time itself. The encouraging reality is that because these influences are rooted in daily habits, they are also modifiable. The brain is constantly responding to the signals it receives from lifestyle choices. When those signals shift towards stability, nourishment, movement, rest, and reduced stress, the internal environment begins to change. Inflammation can decrease, circulation can improve, and neuroplasticity can increase, allowing memory systems to regain strength and flexibility even after years of quiet decline. The most powerful truth about memory loss is that it is not a one-way process. Even when decline has been unfolding silently for years, the brain retains an extraordinary ability to recover when the source of damage is removed. This resilience is built into human biology. The brain is not a passive organ that simply wears out with time. It is dynamic, responsive, and constantly remodeling itself in response to the signals it receives. When the silent poison is identified and eliminated, the conditions that once accelerated memory loss can begin to reverse. At the core of this recovery is the brain's capacity for neuroplasticity. Neural connections are not fixed structures. They strengthen with use, weaken with neglect, and reorganize when the environment changes. When harmful signals such as chronic inflammation, metabolic instability, or toxic exposure are reduced, neurons regain the ability to communicate efficiently. Synapses become more responsive. Memory circuits that were once sluggish can regain speed and clarity. One of the first systems to respond to the removal of harmful influences is circulation. Improved blood flow delivers oxygen and nutrients that neurons depend on for energy. Better circulation also enhances the removal of waste products that interfere with cellular function. As blood flow improves, mental clarity often increases before memory does, signaling that the brain environment is becoming more supportive of higher cognitive function. Inflammation reduction plays a central role in this process. When inflammatory signals decrease, synaptic communication becomes more precise. The brain's immune cells shift from a defensive, damaging mode to a supportive, repair-oriented role. This shift allows neurons to focus on rebuilding connections rather than protecting themselves from constant attack. Memory formation becomes more efficient as the noise created by inflammation fades. Energy stability is another critical factor. When the brain receives a steady supply of fuel, neurons no longer need to operate in emergency mode. Stable metabolic signals support the biochemical processes required for learning and recall. Over time, this stability allows memory systems to regain endurance. Mental fatigue decreases, and the ability to sustain attention improves, creating a foundation for stronger memory performance. Sleep quality often improves when harmful influences are removed, further accelerating recovery. Restorative sleep supports memory consolidation and clears metabolic waste from brain tissue. As sleep cycles normalize, the brain becomes more effective at integrating new information and strengthening existing memories. This process reinforces neural networks that may have weakened during years of stress or inflammation. The hippocampus, once damaged early, is particularly responsive to positive change. Improved conditions can stimulate neurogenesis, the creation of new neurons, in this region. These new neurons enhance memory flexibility and learning capacity. While recovery is gradual, even small increases in hippocampal health can have noticeable effects on recall and mental clarity. Psychological factors also contribute to recovery. When individuals understand that memory decline is not inevitable, motivation increases. Engagement in learning, problem-solving, and meaningful activities stimulates neural circuits that support memory. The brain responds to challenge by strengthening connections, especially when the underlying environment is no longer hostile. Physical movement further amplifies these effects. Activity increases blood flow, reduces inflammation, and releases growth factors that support neural repair. Combined with the removal of harmful exposures, movement helps translate biological improvements into functional gains in memory and cognition. What is often surprising is that improvement does not require perfection. The brain does not need an ideal environment to heal. It needs a better one. Each reduction in toxic signals shifts the balance toward repair. Over time, these incremental changes compound, allowing memory systems to regain capacity that once seemed lost. The process of restoring brain resilience is not about chasing quick fixes or isolated solutions. It is about changing the ongoing conversation between the brain and its environment. When that conversation becomes supportive rather than damaging, the brain responds with adaptation and growth. Memory function reflects this response, improving as neural networks regain strength, coordination, and flexibility, demonstrating that removing the silent poison can transform the trajectory of cognitive aging. Restore confidence in the brain's ability to remember and learn again.